Okay, this is our second big class of practical aerodynamics. Today I would like to talk about making work one, report one, which is devoted to calculation of aerodynamic characteristics and transformation based on experimental data or data from X-foil. I am expecting your questions mostly, but before answering your questions, I would like to show you some example of work one, which I like, and for my opinion, it's very close to what is expected to be delivered as a report one. I already told you that all our representation we must base on good practice, which, for example, could be based on our main book, Anderson, and there you can find how some or all aerodynamic data are represented. Let me share my screen with you. Okay, this is one example which I show you today. You are not obliged to follow absolutely same structure. And I already had several works last semester which had very good quality, and previous semesters as well. And this one is one of them. Is okay. Independently on name, I would like to show you some aspects, and then you let me know if you have some questions. I will try to see your questions in parallel. Summary, you can put, but it's not obligatory to put, where you show main topics in this report: symbols, figures, tables, introduction, experimental data, coefficients, and the transformation of coefficients, and other properties, prototype of airplane, and references. It's always nice to put a list of symbols, even though it's not was not asked. Any scientific paper has some denoted parameters that could be nice to put at the beginning. As again, I would like to clarify that this is not obligatory required, but is always good to have. Same as list of figures and list of tables. This work is based on some template that we have from ABNT. Okay, let's see. Main introduction of airfoil, bibliographic revision where this airfoil is used, and drawing in design modeler. As you can see, can be provided quite a clean figure using standard tool of ANSYS as design modeler. Please remove any possible background on this image, and it's possible to do setting some options inside program of background color. Okay, and these are experimental data. For example, for lift coefficient, doesn't have to be just this way, can be made in a different way. For example, you can combine table 1 and table 2 together. The lift coefficient and drag coefficient could be inside same table. it's very important to put numerical values. Okay. Numerical values are here. They are having same quality as main text, size of text, and color. They absolutely match main text of this report. As I already told you, it's always good to make rounding of numbers. And I expect for you to have, 4 digits or less in your report. Please keep in mind that we do not need long numbers in representation. Okay. This here, it has it has five digits, but because values are small. In this case, could be also written not in floating point, but could be written in engineering units like 1.86, 10 minus 2. It makes shorter this value, but in general it's okay. And also table 3 includes in the same format, includes data on momentum coefficient at 1/4 Hort. You could combine all these 3 tables inside one table is absolutely acceptable. No need to extend so much, but as an example, it also serves. Then author could not find experimental data on pressure coefficient and plotted according to X-foil program. It's accepted, as you know, if you just need pressure coefficient distribution, you can do it. Probably you remember that pressure coefficient is a function of angle of attack and function of coordinate. So I expect something similar that you have several plots on same how we can call it, not a layer, okay, on the same graphic. We have several plots corresponding to different angles of attack. Not obligatory to put so many as here, but at least 5, which you will use in your simulation. I'd like to remind you that we need to simulate zero lift angle of attack, which for this case is close to alpha minus 2, then 0 angle of attack, alpha 0, and close to stall angle of attack near 14 degrees, and 2 more in between 0 and stall angle of attack. No need to put so much data. In general, is enough to have 5 different points. In this case, minus 0, 0, for example, 4, 8, and 12. I recommend you to simulate the last angle of attack, not so deep as stall angle of attack. Could be a bit smaller than stall angle of attack, because models you will use in simulation of viscous flow, they are not exactly precise to simulate flow separation from upper side of the airfoil. So you could simulate also 14, which is exactly stall angle of attack, but if you simulate 12, okay, also acceptable. Even at 12 degrees of angle of attack, you will see small flow separation region. This we can see, I think, from this plot right here. Then you make representation of data, of same data from tables inside graphical format. Please pay attention that graphics should be clean, like you can see here. Black and white background, black axis, right? Also, he used here 2 more axes for plotting drag coefficient and momentum coefficient. So you put 2 additional axes on the side, and you can make all looking nice. Why it's made like this? Because lift coefficient and drag coefficient have very different scale. As you can see here, maximum of lift coefficient is 1.6, but for drag coefficient is 0.02. So much different, around 100 times, right? Oh, less, okay, 60 times more or less. Since they are different, you cannot use the same axis for lift, drag coefficient, and momentum coefficient. I recommend you to use 3 different axes on the same layout. Momentum coefficient is negative. Pay attention that if you have positive or negative momentum coefficient, then put corresponding scale. I hope that it will be not in general a problem to create such kind of picture. And pay attention that numbers should be visible, should have similar size of main text size, right? You can use these 3 colors like black, dark blue, and red. They are nicely visible on white background. And you can also use grid lines to show more precisely data. Is graphical representation always welcome because it's much easier to understand this data, much easier to understand. Okay, so that's it. Let's see. Yeah, so this -2 is close to zero lift angle of attack, -2. Since airfoil is not symmetric, I think it's 5-digit airfoil. Let's see. No, 4-digit airfoil, but it's cambered airfoil, not symmetric. So it's displaced from origin of coordinate. It goes upper. And at zero angle of attack, we have some small value of lift coefficient. Okay. Pay attention also about aspect ratio of your plot. So this such like this, I think it's close to golden ratio, this one, or square. Square plot also is good. In some cases, in some work, I also saw different representation of graphic. This is why I open here another work. This is work from gas dynamics, which you will do other semester. But the general idea is this, that you plot graphics and show numbers on each point also. Sometimes it's quite useful to see numbers. Okay. You can write in English or Portuguese, not a problem at all. Then calculation of missing coefficients. In this case, it's normal and axial force coefficient. Only one comment here that student did not show CA and CA and CL. Oh, CA and CN, and showed just reverse formula. And if you calculate CN and CA at this table, please put correct formula for CN and CA. Okay, our checkpoint here is values you receive. You should be careful with this calculation, because if you or calculate in MATLAB or Excel, by default they accept angle in radians. So you need to make transformation from degrees to radians to obtain correct values. How to understand if values are correct or not? Normal force coefficient should be similar to lift coefficient. Okay, axial force coefficient usually is smaller, much smaller, and sometimes it becomes even negative. Okay, negative is good. It's not so bad. It just has to follow according the formula, according the function you put before. If you make some error in calculation of normal and axial force coefficient, you will see some kind of weird, very weird behavior. For example, this normal coefficient I saw many times, it becomes like a sinusoidal curve. This is when you are using, instead of degrees, you use radians. So you see positive, negative, etc. It means that need to make transformation from degrees to radians, or vice versa, depend on which software you're using, which function you're using. So pay attention that it's important. If you see like a wave instead of line, curve, okay, monotonic curve in such case, it's increasing. In case of axial force coefficient is decreasing, but monotonically decreasing and monotonically increasing. We can assume it's correct. If it's has a shape of a wave, then there could be some problem. Okay, center of pressure according to known relation, when we have moment coefficient at 1/4 Hort. This is equation from our Anderson book, right? Also simply calculated. You also can combine table 4 and table 5. I think there is enough space to put all unknown parameters inside one table. Please also pay attention on following. We do not expect as long report as possible. No, your report can be short, but your report should contain enough information, okay? Enough output in a good format, like compact format. And also you need to write text in between. You can see here in this text, there is not so much, but each table, each part of work is explained. What is done, how it's done. Like this text is absolutely necessary to understand your work. It's not worth to put just tables, formulas, and finish. No, please put text inside so you explain how you understand that some data was obtained, or what you did to obtain one or other parameter. Okay, I think text is important. Do not exaggerate with text. It should not be so big, but always good to put some text to explain what you did. I hope it will be not so long. Then representation, graphical representation of previous tables. This is just to see what is obtained if there is no problem, if there is no error. For example, if we look usually center of pressure, CP, this behavior could be different according to momentum coefficient. Can decrease, can increase, or can have some extremum in the middle. But pay attention also if you have some problem like sudden peak of parameter, then there is some error or in initial data or inside formula. So graphical visualization of this data is important to give reader better understanding and to have double check if your calculation is correct. I would like to remind you that pressure coefficient expected theoretically is near 25%. Depend on airfoil, it will be a bit different, but more or less 25% is what we expect. Here is more than 25%, but not so much. Okay, not so much. So if you start to receive some negative value, of course you cannot have center of pressure negative, like outside of airfoil. So where is the body if your XCP is negative? Outside of airfoil. And also you cannot receive XCP near 1 or more than 1, because if it's more than 1, it means you are also outside of airfoil. Our airfoil is having X coordinate from 0 to 1, from 0 to 1 chord. So it means that XCP cannot exceed these limits. It's expected to be near 25% or close. Also very nice to have graphical representation of XCP. Always welcome when you can visualize this position. As you can see, it explains a lot where the center of pressure for each angle of attack. It helps to present this data very nicely. So you put airfoil inside airfoil coordinates, space coordinates, and point corresponding to each center of pressure at each angle of attack you use for calculation. Okay, CLCD ratio here for your airfoil. I think it's okay, questionable about 8 degrees. I'm not sure that should be at 8 degrees, but maybe for this particular airfoil. Usually CL by CD ratio is more situated on the left. At 0 to 5 degrees, but not at 8 degrees. Maybe for this particular airfoil is here. And here is the lift drag coefficient for complete airplane that uses this airfoil as a profile for wing. Not obligatory to put, but if you found such data, you also can compare. You can see that airplane is very, very different from just airfoil because it has all the structure around, right? Fuselage and other equipments. You remember that for at the end of chapter 1, we had comparison of additional equipment, external equipment around the airplane that increases almost 50% drag coefficient. So this is one or other example. If you have just a wing, you have more than 100 to 1 lift to drag coefficient, but if you have airplane, it's like 20, not more than this. It means that you need to have much more power for flight. If you have full airplane, then you just use a wing. Much more thrust. Okay. And then the velocity of flight for stall condition and for cruise conditions, maximum velocity and stall velocity. This you can do according to my recommendations on the other video. I tell how to calculate these parameters based on Reynolds and Mach number. I don't think I have to repeat. I will just forward you to this video. I can send you. If someone will not find this video, I can send in a comment this video, link to this video. Okay. So that's it. And then references and maybe some annex. There is no annex. Just calculation of aerodynamic coefficient. Very, very simple formulas, right? That allow us to process data. Nothing of complex, nothing of heavy. Very simple, very light calculation. This is why I expect you to do it during first months of aerodynamics, because it's easy, it's simple to calculate. You can calculate basically in few hours, but then it takes some time to write and format. Okay, more time to write and format than to calculate. And again, you can combine data, can combine several tables, right, to make shorter. And you can combine some tables of results, and then it's that's what is expected to have on work 1. Please let me know your questions. I'm ready to answer. Guilherme, please.
I thought Pedro was going to answer first, but I have a question related to the data of my specific airfoil, because I did find the experimental data on the NACA airside and NACA website, but it is only on scanned documents, and the resolution is not actually perfect. So my question is more related to the precision of the data, because I'll probably have to pick it by eye, or have to see and estimate the position of the values. Is this acceptable, or is it necessary to take data from trustworthy tables, like a Excel table or CSV?
Mm-hmm. Okay, thank you for your question. I will try to find a document where I answer this question. Is already explained in one of the videos. I will just try to see where is the link. The idea is following, that all data on aerodynamics usually is old. It's old data because it was developed 50, 70 years ago. Most part of airfoils are known for decades. So since that time, okay, those reports were not renewed, not all of them, right? And data sometimes is old. We can, yeah, we can do it by eye. We know that there are some dependencies. For example, if I go to plot lift coefficient, like here, we see from -2 degrees of, okay, from some negative value until quite significant value of angle of attack, it's a line, it's a straight line. So you will not mistake if you put several points on the same line, straight line, okay? And then you will just need to find out 2 points, for example, maximum 3 points, which are on the curved part. So that helps. For lift coefficient. For drag coefficient is different. It usually looks like parabolic function, very similar to parabolic function. It's not exactly parabolic function. Sometimes it has this deviation according to some process, nonlinear process of flow, which happens. Just give me a moment. I will find link, and I will send. I will try to send in our chat about video where I show how to digitalize such data. You can use several softwares for this. Sometimes I used Excel, just Excel. You make zoom of this plot in Excel, and then you put this picture behind a real plot, and you adjust points on real plot and see how they correspond to picture. Also in Excel, you can make a rotation if you need 1, 2, 5 degrees, depend on if scanned quality is not perfectly aligned with the axis. You can always rotate this plot. I think it's not something that is, how to say, 100% accurate, but we are not looking for perfect accuracy here. I think 2, 5, maximum 5% error is insignificant, is small, because we just study how to do it, right? I never saw some kind of automatic recognition system for plots. Maybe there is. If you found some software which recognizes plots automatically, please let me know. But when I need to do, I do as I show on my video. There is also a way to do it in other softwares, I think, like, okay, just as a guess, in Kachi, I think possible, in AutoCAD, also possible, other drawing softwares, but I like more Excel. There is a reason why. Because according to studies of most commonly used software in aerospace engineering, it was discovered that the most used software in aerospace engineering is Microsoft Excel. Not ANSYS, not Fluent, not MATLAB, but Microsoft Excel is the most common software used. So this is why we can, I think, we can do it. And it works well. when you know how to do, and not difficult, and quite fast, and accuracy is not bad. You can guess these values quite well. Just a moment. Give me a moment. I will stay silent and I will search for this document.
Okay, thanks a lot.
I think this one, and yeah, and this is the list which we have also on Aprender 3 about videos and about all these problems. We can find here something on experimental. Okay. Here on this item 7, we can find comparing the experimental numerical data, and I think in same video I show also, okay, yeah, I show also how to make this transformation from a picture to graphical form. I hope you already know, but if not clear, then you can see this video, right? Questionnaire on Aerodynamics 7 is also same document on our Aprender 3, so you can find a link there. And I say also about report format, about ABNT, about calculation of coefficients for different Reynolds numbers, and many other things. Here, transformation from graphical to numerical data in Microsoft Excel. Exactly the question you ask. Okay, that's it. Pedro, please ask your question.
Professor, I have some doubts about the experimental data that I found, because the data is for 6 spectral radio. Does this influence a lot on the simulation? Because last semester I had some problems. I found the spoil with experimental spectral radio 5, and the simulation for the distribution didn't match. Does the spectral radio influence a lot on the distribution of the velocity, the LCD?
I think there is a problem in your microphone, so it was very hard for me to hear. Maybe others had better sound quality, but for me sound quality was very bad. As I understood, you found experimental data with some value of aspect ratio. Is it correct?
Yes, I'll change the microphone.
Aspect ratio 5. I will open now Anderson book and I will show you what is it here? How does it influence? I hope my screen is still visible for you. And aspect ratio is discussed in one of last chapters of Aerodynamics, so somewhere here in the middle of the book. Just a moment, I will try to find. You, in general response is the following. Here is definition of aspect ratio. You cannot use data from wing to validate flow on airfoil, because even according to this plot, which I showed you today, according to this plot, this is difference when you have infinite aspect ratio, like black curve, and when you have finite aspect ratio for complete airplane. So you see difference. It's many times difference. So I think it's not possible to use directly. But if we go back to theory of aerodynamics and we see definition of aspect ratio as B in square divided by S, where B in square is length of the wing in square, and S is the area of this wing, we can find analytical relation between lift coefficient and aspect ratio somewhere here. Look, like this formula 553, for example. For example, 553. So if you have aspect ratio 5 and you have some known value of lift coefficient, so CL is known, AR is known, you divide, okay, CL by 5 by your aspect ratio, and you receive what is equal A1 multiplied by P. This A1 is a coefficient, which is different for each wing or for each airfoil. It changes, right? So you can find it only dividing CL by known aspect ratio, and then you have this value. And what else? You can, for example, try to multiply, but theoretical aspect ratio is infinite. So if you try to multiply this infinite time, you will receive infinite value of lift coefficient. See, so this is what theory says to us: relation between lift coefficient and aspect ratio. It means that this theory can only be applied to limited value of or limited range of aspect ratios. Just a moment, somewhere here, very close, we have a plot that says about such limits, like this here. It was elaborated by Pranter and team, and after improved. So such formula which I showed you can work efficiently, okay, maybe for aspect ratio 10, for example, minimum 4, maximum 10. If you will try to use it for infinite wing or just airfoil, it will not work perfectly. So this is proving to us that not always possible to make transformation from wing with aspect ratio or experimental data, as we can see here, experimental data, axial force coefficient for wing and airfoil. It's not a good idea. From experience, we know that lift and the drag coefficient for wing and airfoil are very, very different. Very different. Lift coefficient for wing is always much smaller, and drag coefficient for wing is always much bigger. So they both change. In particular, how is the change in this range of aspect ratios we have in real airplanes? We will talk only in chapter 5. It's not a discussion for right now. Okay, so as a practical solution, I recommend you to search data for airfoil and do not use experimental data for wing with some aspect ratio. Okay?
Okay, thank you.
Okay, your microphone improved a lot. I think you changed some microphone settings, right?
changed the microphone.
Great, great. So I hope it's clear. Unfortunately, you cannot use the data from wing to validate flow around airfoil. At least I never saw such valid and reliable tool to make such transformation. Maybe it exists, but then you can search. But I recommend you just search data on airfoil.
Okay.
Please ask more questions. I do not see anyone raise hand. So tell me if someone has questions, we can still discuss. I would like to remind you that it's approaching deadline for work 1. Please let me know if you have questions. Let me check what was set as a deadline. Which day? It's somewhere in 2 weeks. February 17th. Okay, so our next discussion on practical applications could be 18th of February. So it's already after deadline. So when we meet next time, we already should talk about numerical simulation in Fluent and not about calculation of aerodynamic coefficients. Okay, I can wait 1 minute more or some seconds more if you have some questions, so we could talk. And another thing, since today it looks like not so many new questions will appear, since we work only less than 1 hour, we could have such a meeting also next week, because we did not work 2 hours as I planned. So could be another opportunity to talk about work 1, but I will need to confirm with you on Thursday if you have questions, if you need to talk about work 1. Next Thursday we combine if we make class on Friday or not. Gabriel asked question for work 1, are we going to use the airfoil design only in a representative way? What does it mean, a representative way? Of course, no simulations. No simulations, but you need to show picture of your airfoil. You need to show at least what you are going to simulate in work 2. Everything we prepare from point of view of experimental data, we will use this result to validate in work 2. So it's like continuous work, you know. Here in work 1, we prepare for simulation. In work 2, we make simulation in visited flow without boundary layer. And in work 3, we use all previous knowledge to simulate with the turbulence model and boundary layer. But you need to show, like figure 1, you need to show how your airfoil will look like, because in several cases you can have problems to draw. And I recommend you already to make it inside Design Modeler or inside the Space Claim or inside Designer. It's a new tool for geometry design in ANSYS since 2022. You need to show, because sometimes can be a problem to visualize. So if there is a visualization problem of such airfoil, need to pay a lot of attention, because it will impact directly on your simulation. So I prefer to see this image, figure 1, just to confirm if airfoil appears as it should, if it doesn't have sharp edges, if it doesn't have visible edges. Okay, for example, here it looks smooth, right? If it's smooth on its leading edge, very important. Because if there is some artifact inside simulation, it will be absolutely destroying structure of your flow and can generate data very far from what you expect, and you will not be able to compare. So this is why important to show airfoil in work 1. So we confirm everything is good with geometry, and then you continue. Also put your airfoil in a scale that you calculate, right, and that you will use in simulation. Okay. You need to put also scale to show what chord size you will use. Okay, you are welcome. I'm happy to answer questions when they appear. I see no more questions today. Let's see. Let's talk on Thursday, and we decide if you need more answers on some specific questions. Please prepare your work 1. It's already good time to work. Please, Guilherme, ask your question.
Professor, actually, my question. Sorry. Actually, my question is not related exactly to the work, but related to a airfoil that was going to use on the work, but I didn't find any experimental information, so I decided to use another one.
Mhm.
But I was wondering if you know this airfoil and if you know of any experimental information about it. It's the branded D root and tip airfoils that NASA used on a research of drag reduction. I didn't find any information on it, but I was wondering if you know it.
This particular airfoil never worked with. You should know that there are different, let's say hundreds of different airfoils. So no surprise that some airfoils are still not studied by me personally, but the idea is following. Anderson suggests several literatures as a reference for airfoils. Some of them I put in they are open source, right? So I put them in our system for you to download, and you need to make literature review. It's I think a lot of material in open source in open libraries, about a lot of material in good quality publications, but it exists such a problem that performant airfoils and efficient airfoils, let's say modern ones, they are still a secret of some companies which widely use. So they are not published everywhere, these geometries and data. So we can just guess about geometry, but we cannot have exact coordinates. Okay, it's a question of protection of information by some companies that are still using this in commercial applications. So I think it's quite normal. If you could not find experimental data, you need to hurry and find some airfoil which still were not chosen by your colleagues, and make such task, right? Work 1, work 2, and then work 3. It's not important. Not so much important if you chose a new or old airfoil. Work is same. It's just an example. Since it's your first contact with such problem, such study, shape by itself does not matter much. What matters is that your geometry is known and your experimental data is also known. So you could validate it in a nice way, work 2 and 3.
Okay, Professor. I actually dropped that airfoil. I'm using one that has experimental information. I was just wondering if you did know it. But it's okay.
I'm sorry that I cannot help you in this sense, because I have absolutely same access as you do. I do not have any special, let's say, database that companies share with me. I absolutely have same access. I study in and research in internet and in the library, and this is how we obtain data, open data. Okay. Unfortunately, we do not have access to specific databases to use modern airfoils. Maybe it will change in future, but not now.
Okay, thanks, Professor.
You're welcome. Any more comment, please? Okay, see no more comments. Still, we can do next week. We combine if we meet next week, next Friday, to clarify some questions before deadline of work 1. And I would like to wish you nice end of the week, and thank you for participation today. Have a nice weekend, and have a nice work on this weekend as well. See you then. Bye, guys.
Bye-bye.
Bye. Good afternoon.
Bye, Professor. Thank you.
Bye. Bye.